everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering. I'm dealing with the course Computational Aerodynamics. So in today's topic, we will see simpler and Simplec algorithms. So in the previous session, we have seen simple algorithm. Now we are seeing the extension of the simple algorithm and how we predict variables of flow velocity and the pressure and other flow variables we will see especially. Okay, here the simple is semi-implicit pressure linked equation. Okay, so the extension of the simple algorithm are like the simpler and simpler algorithms. So here if we revise, simple algorithm, how it will start is, so the guess value of p star. So the guess value p star. The guess in the sense what? So basically, first you need to know the initial conditions and the boundary conditions for CFD. Okay. So when you are performing any CFD simulation, for that they require initial condition, they require boundary conditions. So to recap, so the initial condition or internal field conditions are nothing but, so you have the grid. So you have here. So this one here, this one. So whatever I have circled, those are called the boundary points. Okay, and whatever I kept dot. So here you can see. So whatever I have drawn as circle, so those are called the boundary points. So whatever I have placed as dot, those are called the internal field points. So here what we need to see is, so the boundary points or the boundary conditions actually are very different from initial conditions. So the boundary conditions are applied for the four boundaries which are present in this diagram. So where let us take the boundary A, B, C, D. So for the boundary A, you apply, let's say, velocity here as 1 meter per second. So what happens here at the inlet, you will have 1 meter per second, 1 meter per second, 1 meter. So every point will have the 1 meter per second. Okay. At the outlet, so you apply a pressure vacuum where at this point P is equal to 0. So P is equal to 0, and here also P is equal to 0 will be there. So at A and C, basically you apply the flow conditions where you have high pressure at the A and low pressure at C, so that flow will move from A to C. So that is what we need to do. Okay, so the boundary conditions actually are applied on the boundary points, which is the circle point. Now, so the initial conditions or the internal field. So here you can see we have dot point. So what is the velocity? So here, if you apply 1 meter per second for the boundary, or let's say at the field A, it does not reflect on this point. This one, this one, this one, this one, this one, this one. It does not reflect on those points. So we have to specially mention what is the value of the initial conditions, or let's say what are the initial values at these grid points, we have to mention. So the we will define the internal point where we call those as the initial conditions or internal field conditions. Okay, so it can be different from the boundary conditions. So we have different types of boundary conditions. So I think we have discussed, but let us recall. So we have Dirichlet boundary condition, Neumann boundary condition, and mixed boundary condition. Dirichlet in the sense, let's say you are giving, let's say u value is equal to 0 meter per second at wall. So we are specially specifying the value at the boundary point. So let's say we have boundary B. So at this point we will give the value of velocity as 0. At this point we will give value of velocity as 0. Okay. So therefore, if we are specifying the value directly itself, then that sort of boundary condition is called Dirichlet boundary condition. Next you have Neumann boundary. So where dou u by dou y equal to 0, let's say. Okay, so here what is the meaning? So dou u by dou y in the sense, so this is slip wall boundary condition. Slip wall in the sense what? So you have all the fluid layers with same velocity. So here the velocity is same u1, u2, u3. So therefore what happens? u1 equal to u2 is equal to u3. Okay, so therefore, so what is happening here? So when you take this u1 is equal to u2 is equal to u3, so the gradient dou u by dou y is equal to 0. So this is corresponding for the slip wall boundary condition. So that is here we are specifying the values for gradient directly. So this is one sort of boundary condition. So other boundary condition, so the mixed boundary condition is combination of Dirichlet and Neumann. Okay, so these boundary conditions are applied for the boundary condition. Next, the initial conditions or the internal fields are applied at the grid points, internal points or interior grid points or interior points. So here, away from the boundary points. So you should not get mixed or should not mix the boundary points with the internal points. Okay, so that is very very important. Now coming back to the algorithm, so guess value. So the guess value, guess p star in the sense. So initially we will guess the value of pressure. Okay, so from there we will solve the value of v star from the momentum equations. So what do you mean by v star actually? So here the meaning of v star is, so whatever the guess value of pressure we substitute in the momentum equation, so from that we will calculate the value of velocity, so which is nothing but v star. Okay, so let's write the momentum equation. So what do we have? So we have dou u by dou t plus dou u by dou t plus u into dou u by dou x is equal to minus 1 by rho dou t by dou x. Let's say we have this momentum equation. Okay, 1D. So let's say 1D apart. Now what is happening? So here you will substitute the value of P star in this equation. So when you substitute the value of P star, so we will get the value of V star from the momentum equations. Okay. So when you get that value of V star from the momentum equation, so what we are doing, we will substitute. Okay, we will introduce a pressure correction P star. So what is P star actually? So we introduce a correction. So whatever we get the P star, so we'll get V star. So again we have a correction factor where we will have to supply for the velocity to get the actual velocity. Then we will substitute that equation into the continuity equation to solve P dash and then actual V. Okay, so with this what is happening is, so you have some whatever the guess value is there, so those guess value we can correct it actually. So after applying some corrections, so we are trying to improve the solution or we are trying to improve the accuracy, then we will substitute them to solve T temperature, K turbulent kinetic energy, E internal energy equation actually. Okay, if it is converged, so basically residue check. So the meaning of residue check is, so whatever the value we have u of, let's say I plus 1 minus u of I modulus. Okay, so the modulus of u of I plus 1 minus u of I, you can say. So the difference between the let's say current step and the different and the previous step. So we will see. Example, I can give you an example where, so the velocity, let's say u2 is equal to 1.23568. Okay, so meter per second. So this is what we have. So u1 is, let's say, 1.20568 meter per second. So here what is the difference between u2 and u1? So it is 0.03. That is what we have. So the value here we get 0.03. So between u1 and u2. Now we will give a condition to stop the simulation. That is nothing but residue. That is called residue. Okay. So the difference between the current step and the previous step is called residue. So where we give a condition usually as 1e minus 5. So the usual residue conditions will be 1e minus 5, 1e minus 7, or 1e minus 8. So basically, if these are the ranges, you can take 1e minus 6 also. So the meaning is the difference between the current value and the previous value should be 10 to the power of minus 5, 10 to the power of minus 6. So it should be less than that. Then only you will stop the simulation. If not, you will continue it. So here, if it is yes, you will stop it. If not, again, whatever the values we obtained at this stage, okay, so we'll take that as the new guess value. So this is the first iteration which we saw actually. So for the first iteration, we have what like we have seen the guess value, then the guess value of velocity, then we get the correction, pressure correction. So from the pressure correction, we'll take the exact value of velocity. Then whatever the velocity value we'll get, we'll solve equation of pressure, and then we'll get velocity. Then we will substitute in other equations of temperature, turbulent kinetic energy, and internal energy, and then we'll substitute in continuity equation to see whether it is converged or not. If it is converged, then we will stop it. If it is not converged, so whatever the values we will get the output from the first iteration. So let's say we have u1, comma v1, comma p1, comma t1. So let's say these are the values of the velocity which we are getting from the end result of the first iteration. So these values will be the new input. So new input in the sense what? So here P is equal to V star gradient. So simply I'll write here it as U1 is equal to U star. Okay. So V1 equal to V star. Next P1 is equal to P star. Next T1 is equal to T star. So whatever the values we get the output from the first equation will be the input for the second iteration. So this loop will keep on running till the convergence criteria is met. Okay. So this is how we solve for simple algorithm. And now, so we have an algorithm called simpler. Simpler in the sense what? An extension of simple algorithm. Okay. So here we have some procedure which is adopted from simple algorithm, which is semi-implicit pressure indication. Semi-implicit in the sense half implicit technique, and it is linked with the pressure equations. Okay, but here what do you know? Like here you have to start, you will have the initial guess values of P star, U star, and V star. Let's say you have the 2D equations of 2D continuity momentum equation. Okay, so we will then solve with the initial guess values to the momentum equation, discretized momentum equation. What do you mean by discretized momentum equation? So let's say you have this dou u by dou t plus u into dou u by dou x plus v into dou u by dou y equal to minus 1 by rho dou p by dou x. This is what we have. Now, what do you mean by discretized equation? We take each and individual term. So how do we write discretized term for dou u by dou t? So this is u of I comma j to the power of n plus 1 minus u of I to the power of n divided by delta t. So this is the discretized term or the discretized expression for the first term, which is dou u by dou t. Then you have dou u by dou x. So for the dou u by dou x, you use u of I plus 1 to the power of n comma j minus u of I comma j to the power of n divided by delta x. Okay, so this is the discretized term for the second one. So these things, like, we will write in the form of linear equations, which is index notation I comma j, I plus 1 comma j, I comma j plus 1. So in this way we write those equations, and we call them as discretized equations. So here what we have, here we have the momentum equation uh, of x and y. Okay, here we have the momentum equation of x and y in the case of discretization method. So here again, whatever x momentum, y momentum equations when we have discretized, from that we will get the values additionally of u star and v star when we take the case value of v. Okay. Now what happened actually? So we will actually use the pressure correction equation. Okay. So these things. Okay. So whatever the values we get from v star, so this thing we will use to solve the pressure correction equation. From that we'll get p dash. Okay. This p dash, okay, will be used to correct the values of pressures and velocity. So where, so the values of u will be equal to u dash plus u star. So sorry, this. So u actual velocity is equal to u star, which is gas value, plus u prime, the correction. So that u dash can be positive, negative. So let's say u star is nothing but you have 2 meter per second. So let's say u dash is minus 0.05 meter per second. So when you apply here, what happens? So u will be equal to 2 minus 0.05. So that would be 1.95. Okay. So this is 1.95 meter per second. Okay. So what is happening actually when the correction can be, so here I have just given an example. So the correction can be positive, can be negative. So why? Because the it can over predict or it can under predict. So that is why. So whatever the corrections we get, we'll just add it. The magnitude value or the sign, it will take care of it. Okay. So here you can see u star is equal to u is equal to u star plus u dash. So this one we say it as actual velocity. This one is called guess, and this one is called the correction. Okay. So basically, what we get? So actual value is equal to guess plus correction. Okay. So the actual value is equal to guess plus correction. Fine. So here, what do we have? So the actual value is, let's say, p comma u comma v, and the guess value is p star, u star, v star, and the correction value is, let's say, p dash, u dash, v dash. So these are the correction values. So again, what is happening? So to start the procedure, so initially we are guessing the value of p star, u star, v star. We'll substitute them in discretized momentum equation. Then we will get the values of u star, v star, those aspects. Then we will use those terms to solve the pressure correction equation. Okay. So with the pressure correction equation, so then what is happening? So here the pressure correction equation, you will get an output which is p dash. With that p dash, again you will solve the velocities, and you'll get u and v. So in between you'll get u dash and v dash also. Then that you'll substitute such that you'll get actual values of p, u and v. And then you check the convergence criteria. Okay. So if the convergence criteria, how we check actually? So we'll substitute these values in continuity equation. So what is continuity equation we have? So dou u by dou x plus dou v by dou y equal to 0. So this is a continuity equation which we have. So how do we write the discretized equation of the continuity equation, so we use the index I and index j. So therefore, the index I and j can be used to write the continuity equation. So here you can see u of I plus 1 comma j minus u of I comma j divided by delta x. So this is the discretized form of continuity equation, plus next v of I comma j plus 1 minus v of I comma j divided by delta y equal to 0. So this is the second continuity equation. Now what is happening actually? So whatever equation, like whatever the values we have here, so value of p, value of u, value of v, will substitute here in the continuity equation. So the values which we get at the end of the pressure correction and velocity corrections will substitute in continuity equation. That is called the convergence check. So here the convergence check is performed in this way. So once the convergence check has done, so basically when you substitute, what happens? So let us take the I value as 1. So j value as 1. So what happens actually? So this will result u2 minus u2 comma 1 minus u1 comma 1 divided by delta x, plus next v1 comma 2 minus v1 comma 1 divided by delta y equal to 0. So these values we will substitute there. So when you substitute, so when it is equal to 0 is what? It is very it is even less than 1e minus 5, 1e minus 6, that is what we have. So but in the numerical simulations, we have always error. Why? What is that error coming? Where it is coming? How it is coming? So the error is called truncation error. So already we have discussed in the previous modules. So for the finite difference method, we have truncation error. That is for sure. So never ever your value or the residue will not be equal to 0. It will be always having 1e minus 4, 1e minus 5, like that it will have actually. Okay, never ever. So it will be 0. Okay, so what happens actually? So the residue term, whatever we get, that term will act as an error term actually. So basically when you substitute equal to 0, so when you substitute values here, u21, u11, 12, 1, u11, v11, so this value whatever we get, it is, let's say 1e minus 3 you'll get, or 1e minus 4, 1e minus 2. So if you get value, let's say greater than 1e minus 6, we will start again the simulation. How? Whatever the values we get, we will take those as the new guess values. So here the simpler algorithm what we have, so we are solving additionally a discretized momentum equation when you see the simple algorithm. Fine. So we have one more algorithm which is called Simplec. So here actually, so before starting the guess discretized equation, so this point, so with the initial guess values, you get actually pseudo velocities actually. So here the changes what we have from the Simplec algorithm I am just telling. So we basically it has started or evolved from the simple algorithm itself, which is called semi-implicit pressure linked equation. From that we got simpler, and from simpler we are getting Simplec. So whatever Simplec is there, the small modification to obtain accuracy. What modification is? When you get like the guess values of pressure, velocity, what we are doing is we are directly substituting it in discretized equation for other techniques. But here what we do is, so we will substitute in the momentum equation to get we call it as pseudo velocities. So whatever the guess values we have, we substitute in momentum equation to get u cap, v cap. Okay. So this u cap, v cap, and p cap. Let's say these values will go into the discretized form. From that, the what do you say, the algorithm will start. Okay, so this is one additional step that is being used for the Simplec algorithm. So there is a concept called pseudo velocities. So whatever the guess values we have, so we will use it for the momentum equations. From that you will get a pseudo velocity and pressure. So these values will be an input for the discretized equation. Okay, so there is a step in between the guess value and the discretized equation, so which we are getting by incorporating the momentum equation solving using pseudo method, or let's say to obtain the pseudo velocities. Okay, so by this what we have, so we are actually trying to improve the accuracy of the guess values. The procedure is same, but here the extra step what we are doing is like we are calculating the pseudo velocities or pseudo uh, variables for pressure and velocities. So with this, what is happening? Like it will improve the accuracy. The remaining procedure it would be mostly same. The major changes what we have is, so we will calculate the pseudo parameters. So with that you will get some accuracy. Okay. So with that we have compared the simple algorithm which is semi implicit pressure linked equation with Simplec and simpler. So the differences what we have seen is, in simple algorithm it's very straightforward. So initial guess value will directly go to the momentum equation to get values of pressure. From that you will get correction. That correction will go for the velocity correction. Then you will get actual velocity. That velocity we will substitute in continuity equation. Then we will get the residue. We will check the residue whether it is less than 10 power minus 6. If it is greater than 10 power minus 6, we will continue it to perform simulation. That is for simple algorithm. Simply what we have, so additionally we will use the discretized momentum equation to solve. Okay, and simpler, like that is simpler actually. Simpler what we have, so we have pseudo velocities actually. So for the pseudo parameters, so whatever the values we get guess it, so that will be used for solving momentum and momentum equation to get the pseudo values of velocity and pressure. Then that values will go for a discretized equation of the momentum, which is same as the previous algorithms. Okay, so the standard procedure is same. To check the convergence criteria, you have to substitute in continuity equation to check whether the residue has come very less or not. If it is not come, you will keep on iterating it with the new values of P, U, and V. Okay. So this is all about the algorithms of simple, simplex, and simple. In the next session, we will see we have piezo algorithm, pressure linked e-splitter operator actually. So and pimple algorithm. So which basically the simpler algorithms are used for steady state solvers. So when you want like transient solvers, so piezo pimple algorithms, so they are used for the transient solvers. So we'll see about those aspects in the next module. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.